Okay, so welcome back to another video. So in today's video we have the following limit. The limit as x approaches 0 of 1 minus the product from k equals 2 to n of the kth root of cosine of k times x divided by x squared is equal to 10. And now we're being asked to solve for n, which is what is our our max index. So of course, straightforward if you want to evaluate this problem, which actually, yes, this is actually going to be the first step. If you actually try to evaluate this limit as x approaches 0, you're going to get that this is actually an indeterminate form. So, and then using that fact, we'll be using a couple techniques such as using L'Hopital's rule and then rewriting this whole expression, even converting from the product rule to using sums as well. And eventually we'll reach the goal that n will equal a certain value to help make this expression true. So now, with that starting, of course I'll let L, we're going to let that equals the given expression. So we'll let that approach 0. And of course, let's see, this n, k equals 2. So this is the kth root of cosine of kx, and then divided by x squared. So you'll see that, of course, if I evaluate this as x approaches 0, we get that it's a 0 over 0 indeterminate form. So now what I can do is, by applying L'Hopital's rule, let me write L'Hopital hospitals, however guys you want to use it. Then that means I have to take the derivative from both the derivative of the top and the derivative of the bottom. So of course I'll write this as, so this is still a limit, and then this will be d over dx of, so we know the derivative of 1 is just 0, so we don't need to worry about that. And also, since it's a negative out front, so what I'll do is that I'll actually move the negative outside in front of the limit. So this is negative, and then now we have the product series from, now of course, k equals 2. Well, we're basically just rewriting the same thing. And also, since this is the k root, I'll actually write that as a term as an exponent. So this is the cosine of kx, and then to the power 1 over k. And that's just being divided by the derivative of x squared, which is just 2x. What I'll do is I'm going to let this, the numerator, well, really, the inside expression of our derivative, I'll actually define that as y equals, of course, our product series, our partial product series. And I'm actually missing parentheses, though. Okay, that's good. So then what I'll do is we're actually going to perform a logarithmic differentiation. But before we get to that step, how about we take the natural log of both sides? So I'll take the natural log of y, and then I'll set that equal to the natural log of the whole product series. Let's see, k equals 2, and of course cosine of k times x, then 1 over k. We'll also now rewrite this right hand expression, set that equal to. So we write this, instead of a product series, we can use that as a summation series because of the continuity of that. So that means this is the infinite sum. This is going from n, and then this is from k is equal to 2. Okay, so, and then I'll just move the 1 over k to the front. We're just using like our rules of natural logs. And then this is the natural log of cosine of k times x. Okay, so now we have the natural log of y, and using the implicit differentiation, I'll get 1 over y, then multiply with dy over dx, and we'll set that equal to, so this is negative since we have the natural log of cosine, so it's 1 over cosine kx, and then derivative of the inside, which is just k times sine of kx. The k's will cancel, and I'll just move the negative symbol outside, and our index will start at k is equal to 2, of course. And we have a sine over cosine kx, so I'll rewrite that as the tangent of kx. And then we keep going further. This is, well, I can just multiply the y, so we'll end up with just a dy dx on its own. So let's see, this is dy over dx. This is equal to negative y, then multiply with the infinite sum, or not the infinite sum, the partial sum, from starting from k is equal to 2, and then the tangent of kx. So now we know that therefore this is actually just equal to the derivative of the product series over here. So I'll actually write it as d over dx. I'll just rewrite the same thing what we were given before. So the product series k is equal to 2 of what's the cosine of kx. This is 1 over, well, yeah, I really should have just put the 1 over k first and then the closing parentheses. And so we know that that's actually equal to negative y times the partial sum, then k is equal to 2, tangent of k times x. Okay, so we know that. So now let's actually just plug some things back in. So now rewrite that L is equal to, so we had the, from before, it's the negative limit as x approaches 0 of the derivative, which we show that's here, and we have a negative y. So what I'll do is I'll substitute that y what we have. So this is the negative, so we have that this is negative partial product from k is equal to 2 of the cosine of k over x, and then really just 1 over k. I should have put a extra parentheses like this. Okay, that's better. And we multiplied that with the infinite, the partial sum. So this is from k is equal to 2 to n of the tangent of kx. And that's still being divided by the derivative, which we said that was 2x. Okay. And now continuing further, I can factor out the 2 from here. That'll be a 1/2 outside. And then we have the negatives cancel, so that's nice. And now we just take the limit as, let me actually write the parentheses first. So we have big parentheses. So this is the limit as x approaches 0 of the product series. Let's see, k equals 2. Then, of course, we're still writing some stuff, just like before. 1 over k, and then that's being multiplied by our sum, but of course I can actually take the limit as that as well. So this is the limit as x approaches 0 of tangent of kx, and then divided by x, which is just from here. We just moved it over here, so this is a product, so this is okay. Now the next step is, now if you were to take the limit as x approaches 0, so over here, cosine of k times 0. So any for the input 0 and then multiply with a scalar, if you take the cosine of that, it's always just going to equal 1. So 1 to any power is just always going to be equal 1. And if you take that product series, 1 times infinitely matter with times 1, then you're just going to get that this whole limit evaluation of the product series is just going to equal 1. So that's really nice. So we have now 1/2 multiplied by 1, and now multiply with our partial sum series. Let's see, now this is still, we haven't evaluated the limit on this one yet. So tangent kx, and then divided by x. And now the next step here is I'm actually going to multiply and divide a k over here. So okay, let me just rewrite this first. Let's see, 1, and then now the infinite sum or partial sum of the limit as x approaches 0 of k times, and I'll just factor out how about this? Let me just factor out the k here, because that's what we can do. And then now we have the limit as x approaches 0 of tangent kx, and then divided by, or actually it's supposed to be kx because we multiply and divide, so. And then over here we know that we can use the fact that the tangent of kx divided by kx, or really the tangent of x divided by x, we know that we can use the rule that it's actually going to equal 1. So that means 1 times k, and if you take the, so let me just rewrite this again, so write the next step. So this is 1 over 2, then times 1, and then if we take the partial sum, n from k is equal to 2 of k times 1, or just k, then you use the rule for the sum of k numbers is actually can be written as 1/2, and then multiplied with n times n plus 1 divided by 2. But since our index starts at 2, we have to consider the term for 1. So we actually have to subtract 1 from, because this is the general formula when you start with k is equal to 1, but since we start at k is equals 2, we have to subtract that. So now the last step, of course, I can just rewrite the get a common denominator. And if I do that, I can actually, this is actually the same thing as written as n times n plus 1, subtract 2, and then divide it by 2. Then we have that this is 1 over 2, then times n squared plus n, and then minus 2 divided by 2. And just distribute the 1/2 into here, so n squared plus n minus 2 divided by 4. And we set that whole equation equal to 10. So now going from over here, if we were to solve for our n value, we get that this is n squared plus n minus 2 equals 40. Then I can actually solve this for 0 for n, so plus n, then subtract 40, so minus 42 equals 0. And then we have that, we can factor this out as n plus 7, n minus 6, and then we get that n is equal to negative 7 and 6. However, since we're dealing with the product series as a max index and we start at k is equal to 2, we can't have a negative, so of course you can just exclude that solution over here. And therefore we have that the final answer is that n is equal to 6, like so, in this red box over here. Okay, yeah, so yeah, that's pretty cool if you ask me.